The complex impedance can best be described as a generalization of the resistance R. The complex impedance of a resistor ZR is simply the resistance R. The complex impedance of a capacitor C is 1 divided by j omega C, where omega is the frequency and C is the capacitance. And the complex impedance of an inductor ZL is j omega L. The impedance of a resistor R is a real number, and the impedances of capacitors and inductors are imaginary numbers. When using complex impedances for resistors, capacitors, and inductors, together with phasor notation for AC currents and voltages, we can solve AC circuits very easily because all the laws we already derived for DC circuits apply in the same way. Consider, for example, Ohm's law. Instead of a resistor, we'll have now an impedance Z, a voltage across the impedance, V, and a current through the impedance, I. Then, same as Ohm's law, V is equal to Z times I. This holds true for all impedances. This could be a resistor, the impedance of a capacitor or inductor, or even combinations of them. The formulas for the standard circuits, such as the current divider or the voltage divider, also work the same way for AC circuits as long as we use complex impedances and phasor notation. To demonstrate this, consider the following example, where we have an AC voltage source which produces Vs, a capacitor, and a resistor. Let's say we want to find the voltage across the resistor, Vr. Assume that Vs is already given in phasor domain. We're given C and R. The first step is to transform this circuit into a circuit with complex impedances. We substitute C by the impedance ZC, which is 1 divided by j omega C. And we substitute R by the complex impedance ZR, which is equal to R. We can now use the voltage divider formula and we'll get VR equals ZR divided by ZR plus ZC times Vs. Now let's substitute ZR and ZC. Which leads to in order to express VR as a phasor, we need to find out the magnitude or the length of the phasor and the phase. For this, we need to calculate the magnitude of j omega RC divided by j omega RC plus 1 and the phase of j omega RC divided by j omega RC plus 1. For the magnitude, first note that this is equivalent to absolute value of j omega RC divided by the absolute value of j omega RC plus 1, which is omega RC divided by omega squared R squared C squared plus 1 and the square root of this. For the phase, first note that this is equivalent to the phase of j omega RC minus the phase of j omega RC plus 1. The phase of the purely imaginary number j omega RC is simply pi half. And the phase of the complex number j omega RC plus 1, which is given in rectangular form, is the arcus tangens of the imaginary part, in this case here, omega RC, divided by the real part, which in this case here is 1. Now let's assume that the phasor Vs doesn't have a phase. Then VR in phasor domain is equal to omega RC divided by the square root of omega squared r squared c squared plus 1 times Vs with phase pi half minus arcus tangens of omega rc. If we wanted to convert this back into the time domain or into the trigonometric form, we first would need to know which sinusoidal signal we used. Let's assume that we used a sine. Then Vr of t is omega rc divided by omega squared r squared c squared plus 1 square root times magnitude of Vs sine of omega t plus pi half minus arcus tangens of omega rc. Note that we assume that Vs is the length of the phasor of the source voltage, Vs. So if we want to write Vr in the time domain or as a sinusoidal signal, we again have to multiply with the square root of 2.